The concavity of a function refers to the shape of its graph. There is more than one standard way of defining concavity, and they all turn out to be equivalent for nice functions. In this video, I want to explain what the most common definitions are. As motivation, let's look at this family of graphs. By looking at the graph of y equals x to the a, where a is a constant. Right now a is 1, so I have y equals x, and the graph is this straight line. But if I change the value of a, then the graph changes. For example, when a equals 2, I know I get a parabola, like this one. But actually, for all values of a greater than 1, I get curves that all look a little bit like a deformed parabola, maybe more or less bent. But I want to say that all these curves are similar, they all have the same shape. On the other hand, if I take values of a less than 1, then all of these curves have a different shape. So we are going to say that these curves have one type of concavity, or shape, and these other curves have a different type of concavity, or shape. And when we ask about the concavity of a graph, we're asking whether it looks like this, or perhaps it looks like this. The two graphs that I am showing on the screen are the two models for the two types of concavity. We are going to call curves that look like the one on the left concave up, and curves that look like the one on the right concave down. As a warning, if you study with old textbooks or if you're learning math in French, then you're probably calling these two concave and convex instead of concave up and concave down. Except which one is concave and which one is convex may depend on the author, because it depends on whether we look at things from above or below. I prefer concave up and concave down. Of course, I would like to have a better definition than saying, does the curve look like the one on the left or the one on the right? So I'm going to look at these two shapes and try to understand what are the geometric properties they have that may lead us to write a nice formal definition. I'm going to do that in three different ways. First idea. Here I have the graph of a function that I want to call concave up. And I have chosen 2 points on the graph, and I've drawn the segment of the secant line between them. And what I notice is that no matter what these 2 points are, the segment of the secant line between them stays above the graph. By contrast, here I have a curve that I want to call concave down. And if I do the same thing, if I pick 2 points on the curve, and I draw the segment of the secant line between them, then no matter what these 2 points are, the segment of the secant line stays under the graph. Using this idea, we have our first candidate for a definition for concavity. We can say that a function is concave up when secant segments stay above the graph, and concave down when the secant segments stay below the graph. And this works well, and it has a nice geometric motivation behind it, but I would like to make it a little bit more rigorous than this vague statement about being above or below the graph. And we can do it. With a little bit of geometry and algebra, we can transform this into a precise mathematical statement. But I won't do this now, because this is not the definition I am going to use. Instead, here is a second different idea. Instead of looking at secant segments, let's look at tangent lines. Here I have the graph of a function I want to call concave up. I've chosen a point on it and drawn the tangent. And look at what happens if I look at all the tangents. No matter what the tangent is, the graph of the function always stays above the tangent lines. By contrast, this is the graph of a function I want to call concave down. And in this case, the tangent lines always stay above the graph of the function. I can use this second idea and produce a new candidate for the definition of concavity. I can say that a function is concave up when the tangent lines stay below the graph, and a function is concave down when the tangent lines stay above the graph. And like for the first idea, I should now do a little bit of algebra and geometry to transform this vague sentence into a precise mathematical statement. I could do that and it works, but I won't, because this is also not the idea I'm going to take. I'm going to look at a third way of doing it, and that's a definition I will stick with. I'm going to look at tangent lines again, but now I'm going to focus only on the slope of the tangent line, which is the slope of the curve, and how it changes. I'm going to start, in this case, with a concave up function and a point on the left, and I'm going to move it and see how the slope changes. Notice that here the slope is very negative, and as I move the point towards the right, the slope becomes less negative, eventually 0, now positive, and now it keeps growing. So in this case, in the concave up function, the slope increases. By contrast, I now have a function I want to call concave down, and if I start with a point on the left, the slope is very positive, and as I move the point towards the right, the slope becomes smaller and smaller, then 0, and now negative and more negative. So the slope is now decreasing. Using this idea, I can define a function to be concave up when the slope is increasing, and concave down when the slope is decreasing. And an advantage of this definition is that it is simpler, because the slope is a derivative. So I'm saying concave up or concave down means the first derivative is increasing or decreasing. So I have found 3 possible ways of defining concave up. Are they different? Either secant segments are above the graph, or tangent lines are below the graph, or the slopes are increasing. And they all should be rewritten into something more formal. Well, the good news is that for nice functions, for differentiable functions, all 3 are equivalent. The proof of this relies on the mean value theorem. That should not be a surprise because everything requires the mean value theorem. I'm not going to write the proof, but they're all equivalent. So you could take any one you want. Most calculus textbooks use number 3 as the definition. The advantage is that it is simple. Number 1 and 2 have a nice geometric intuition behind them, and to a certain extent, number 1 is the best one. The advantage of number 1 is that it makes sense even when the function is not differentiable, so it's a little bit more general. If you study analysis at a higher level, you will definitely encounter the first one. But for the purpose of calculus, we can make do with number 3. So that's the one I'm going to use as a definition. I'm going to say that given a differentiable function on an interval I, the function is concave up when the first derivative is increasing, and is concave down when the first derivative is decreasing. And there are some special points, the ones where concavity changes from one type to the other. We're going to give them a name. We're going to call them inflection points. Inflection point is an interior point where the function goes from concave up to down or vice versa. For example, in this graph here, to the left of the point we have concave down, and to the right we have concave up. If we want to be a bit more formal, we can say that changing concavity at a point means there is an interval centered at the point such that on the left-hand side it's concave up, on the right-hand side it's concave down, or the other way around. We can also say that an inflection point is to concavity like a local extremum is to monotonicity. A local max or local min is where a function changes from increasing to decreasing or vice versa, and an inflection point is where a function changes from concave up to concave down or vice versa. Inflection points also have a nice geometric property that allows us to identify them. In this example, I have an inflection point, and I'm going to look at what happens to the tangent lines. To the right of the inflection point, the function is concave up, and so the tangent lines are staying below the graph. To the left of the inflection point, the function is concave down, and so the tangent lines are staying above the graph. What happens at the inflection point? Well, at the inflection point is where the tangent line exactly crosses the graph, because it stays above on one side and below on the other side. And this gives us a nice way to identify inflection points on a graph quickly. To conclude, we have a couple of theorems that in practice is what we use most of the time rather than any definitions. Just like increasing doesn't mean positive derivative, but if a function has positive derivatives then it must be increasing, we can do something else with the second derivative. If I have a function that is twice differentiable on an open interval, and the second derivative is positive, then that means the first derivative must be increasing, which by definition means the function is concave up. And if the second derivative is always negative, then the function must be concave down. What happens when the second derivative is 0? Those are the candidates for inflection points. So if I now have a function that's differentiable on an interval and an interior point, if the function has an inflection point at it, then the second derivative must be either 0 or not exist. Notice that this does not say that second derivative 0 implies inflection point, it's the other way around. In summary, just like first derivative positive or negative guarantees increasing or decreasing, and first derivative 0 gives us the candidates for local extrema, second derivative positive or negative guarantees concave up or concave down, and second derivative 0, or does not exist, gives us the candidates for inflection points.